Hello and welcome back to Data Analysis and Visualization. I'm Jovita Christie, and as I had mentioned in the previous video, I'm back this time with linear regression implementation, as well as an introduction to OLS, which is ordinary least squares, used to minimize the random noise or error generated while trying to fit your data on a linear regression line. So let's begin. Now, what are ordinary least squares? You already know that linear regression is a method for modeling relationships between a dependent variable and one or several independent variables in order to discover and quantify the strength of important correlations between them. Now, you should use OLS, which is ordinary least squares, to fit this line if your goal is to construct a function that's a close approximation of the observational data. So if you want your line to be really precise and a very close approximation of where your actual data points lie, then you should be using the OLS method. But you should, as always, expect that the actual values are not going to be identical to the values predicted by the regression line. And this is because values predicted by the regression line are simply estimates that are more similar to the actual values in the model. You cannot really expect your model to give you the exact value. It would, however, give you a close approximate value. Now, OLS is particularly useful for fitting a regression line to models containing more than one independent variable, that is IV. And with the fitted regression line, one obvious purpose is to estimate the value of the dependent variable given the values of the independent variables. So usually it's not just about creating a regression line, but most of the time it's about how that regression line is going to help you to make predictions. If you're given the values of all your independent variables, then how do you make predictions about your dependent variable? So that is the main purpose of creating regression line. And so OLS works very well if you have several independent variables. When you're using OLS to fit a regression line that has more than one independent variables, two or more of the IVs may be interrelated. Now, this could be something that you need to consider, that your independent variables might also be related among themselves. For example, if you were trying to predict something about a car and the independent variables were, say, the size of the car and also how much petrol you can fill into that car or how much fuel you can fill into that car. So obviously the size does matter. Sometimes a car that's bigger has more capacity of holding fuel, or a vehicle in general that is bigger can hold more fuel. So in this case, you're trying to predict something about the car, maybe about the cost of the car or something. And these are the two variables that you are taking into consideration. Now, these are supposed to be independent variables helping you to predict the dependent variable, but those two variables are interrelated. They are related among themselves because obviously a car that's larger might, not might, but would definitely have more capacity to hold fuel. And so independent variables could also be interrelated among themselves. And when they are strongly correlated with each other, then it is known as multicollinearity. So let's see a little bit more about that. Multicollinearity tends to adversely affect the reliability of the IVs as predictors when they are examined apart from one another. So if you would try to examine these variables apart from one another and try to predict how each variable affects the dependent variable separately, then that would affect the reliability of your IVs, of your independent variables. So luckily, this multi-collinearity doesn't decrease the overall predictive reliability of the model when it is considered as a whole. So you should use all these variables together and create a regression model in order to understand how it affects the dependent variable. So if that is the case, then multi-collinearity is not a problem. Now, in addition to using OLS to perform fitted linear regressions on your models that contain more than one IV, you can also use it to perform statistical tests. Okay, so you can also use this type of regression not just to predict things, but you can also use it to perform statistical tests like a hypothesis test, which you will be seeing in the next video. So either the next or the next video where or the next to next video where you will be studying how exactly this statistical test works when you are working with linear regression. So here I'll just give you a simple example of how hypothesis testing works. So imagine that you're a manager of a major chain store trying to decide where to locate a new store. So you already have a couple of stores. It's a chain, so you have many stores, but you want to create or start a new store somewhere. And so you're trying to find out the location, a suitable location. So you're pretty sure that while finding this location, there could be two factors that strongly affect the profitability of your business. One factor is the mean income of the local population, and let's call it X1. The second factor is distance to the nearest store belonging to your primary competitor, and let's call that X2. So there are two factors which you feel are going to affect the profitability of your business, and one factor is the mean income of the local population. What is the average income of the people living in that area? Obviously, if people are earning more, they'll tend to buy more from your store. And the second one is the distance to the nearest store belonging to your primary competitor. If you're trying to build, say, a petrol pump, you don't want to build it next to somebody else's petrol pump because that would then cause issues, profitability issues. So you always want to see where your nearest competitor is having a store so that you can measure that distance. Now you create a regression model by using data from all your other stores to see if these variables are statistically significant predictors of profitability. So you're not just going to go with your intuition in this case. You already know that these two might be X1 and X2 that we saw earlier might be actually statistically significant predictors of profitability when it comes to deciding a location for a store. But you still want to be sure, you want to test that hypothesis. And so you create a regression model to test the hypothesis by seeing the data from your previous stores. So you already have so many stores. Now you just find out data about all these stores, finding out what the average income is of the people around, what is, you'll also try to find out where the nearest competitor's store is located, at what distance from your other stores. So you'll do that. And before you do that, you'll formalize your guesses as a hypothesis in the following manner. So first, hypothesis one is that a store's profitability increases as the local population's mean income rises. So this is the one thing that you are assuming and you want to prove or disprove, whatever that is. So that is that if the people's income around your store is average income is more, then your profitability of the store is also going to be more. And the second hypothesis you're stating is that a store's profitability increases as the distance to the nearest competitor's store increases. So obviously you don't want your competitors' stores to be very close to yours. And so your profitability would definitely increase if your store is away from your competitor's store. So this is the second hypothesis which you want to test. Now, whenever you create a hypothesis for testing, you always have to create a null hypothesis. For every alternative hypothesis, you need to have a null hypothesis. You'll learn about this in the next couple of videos. So don't worry if you do not know what a null or alternative hypothesis is right now. But it looks something like this. So this is what a null hypothesis would look corresponding to the alternative one about local population's mean. And this is what it would be, that the local population's mean income has no effect on store profitability. Your hypothesis is that if the average income is higher, your profitability is going to be higher. But the null hypothesis would be that the average income has no effect on the store's profitability. And the second null hypothesis, corresponding to the distance alternative hypothesis, would be that the distance to the nearest competitor's store has no effect on store profitability. So this is your second null hypothesis, that distance doesn't matter. The first one is that average income of the local population doesn't matter. Now, if you wish to get meaningful results from your analysis, then you need to make certain assumptions about your data. And that those assumptions would be that the epsilons, I talked to you about epsilons, which is sort of a noise or error that your regression line produces because your data points are not exactly falling on the line. So these regression errors for each observations should be normally distributed. You want them to be normally distributed, not any other probability distribution. And the regression errors should average out to 0. And the regression errors should have approximately the same amount of variability. So if your data does not meet all these specifications, then a linear model might not be an appropriate one for your data. And you might want to go for some other model like a curved line or something that we're going to see a little bit later on. So that's what you need to do in this case. And now I'm going to take you to my Jupyter notebook where we are going to see how you can implement linear regression. So we are going to do a program of linear regression on Olympic 100-meter gold medalist. So the timing that they took. And this is what we are going to do here. You can pause the video whenever you like, and try to run the code in your machine. Once again, you don't have to do anything. You don't even have to install anything. You can just go to Google Colab and just start a Jupyter notebook and start running the code. You don't even have to install or worry about installing any of these libraries that I'm using here. So we are going to import, and the import is going to, we are going to import pandas as usual, NumPy library, and cpon library, which we're going to use a little bit later on, and matplotlib in order to plot the data once it's ready. So from matplotlib, we are going to import pyplot. So that is given here, and these are all the names that we will be using in the code. Now, this is the file that I'm using. I have linked it down below, so you can also directly use this link in your code. So you can see in the description box, this link is available. This contains a file that contains the year, and in that year, what time was the time taken by the gold medalist in the Olympic 100-meter race. So, it's a CSV file, so we are going to use pd.read_CSV and name of the file, which is here. So that would read this file, and then I'm doing df.head and printing the 40 values. There aren't really 40 values, but I just want to print all the values, so it's right here. You can see the year is given, which is 1896, and the time, which is 12 seconds. So in 1896, the gold medalist in the 100-meter Olympics running race managed to finish in 12 seconds. And then you can see as the years progress, that time is decreasing, right? So the most recent one, 2016, is 9.81 seconds. Before that, 9.63 seconds. I think that was Usain Bolt. if I'm not mistaken. So this is the data, and we want to create a regression line for this data. And then we want to predict what would be the timing for 2020 Olympics. So that's what we're going to do. Now, this is, first of all, you need to format your data into a correct shape. This is necessary because the function linear regression model that you are going to be using from sklearn library, it requires the data to be in this format. So you can see what I'm doing is I want to distribute these two columns into x and y variables. So year is going to be x and time is going to be y, because time is going to be dependent on the year. So when I want to predict what will happen in 2020, then time has to be the dependent variable and year has to be the independent variable. So that's what we are going with. So to turn x into year, you need to do it in this manner. You need to write x and then df year data frame and pass year as the column. Then you are doing x train. So this is your data that you want to train your model with. So x train is equal to np.array x. You're converting that data frame and reshaping it. So you're using the reshape function and passing -1 and 1. What this does is converts your data into these two dimensions. You can see now your data contains 29 rows totally and 1 column. So you want that to be in this dimension of 1 column, which is why you're passing -1 and 1. That's what the reshape function will do. Then you have the Y train, which you're creating, and this time you're using the time. You don't need to reshape this one. It would look like this currently. It has 29 values inside. So this is what it looks like, and it's not two-dimensional like X. So we have X and Y ready. Now we are going to create the linear regression line. So for that, once again, I'm going to import NumPy. I'm also going to import, oh, I just forgot to run this code for you. Let's go back and run this. So this is the first part of the code which I'm running, and it might take a little while depending on your internet connection. Okay, I think it's producing, yes, producing the result. So finally, this is the result for this. And this is the code for which we found the shape. So you can see 29, 1, and here it will be just 29 because I'm not changing the dimension here. And now we are going to take the sklearn library and get the linear model from there and import linear regression to create our object of linear regression. To do that, we just have to take a variable, we'll call it model, and just write linear regression. So this would create an object of this type. And then you try to fit our input data, fit the input data into this model. For that, the function is .fit. So model.fit and pass those x train, which was here, and y train variable, which was here. Pass those two here, and then you just have to perform your predictions. So now you're going to find out your predicted values of y by doing model.predict x train. So you're passing all your x values and trying to predict all your y values because you want to create a regression line. So that's what's happening here. And then PLT, if you remember, PLT was something that we got here. PLT, that was pyplot. So pyplot is what you're going to use in order to create your graph. So in that, there is a function scatter, with which I'm going to pass x train and y train, which are the actual points. So these blue things that you see, this is the graph that is created, by the way. And these blue dots that you see right here, those are the dots that are your actual X and Y values. Okay. And then the next one that you're doing dot plot, which you're using to create this red line. That is why you will pass X as usual. X will be the actual X, and the next thing you're passing is Y underscore predicted. So this is the Y that you predicted using your linear regression model. So that is the predicted Y, and color R just means you want it to be red. So this is the line created. You can see it's quite close to all the data points, except this one that's really far away. But other than that, this line is quite close to most of your data points. Now let me run this one. Okay, it's the same. And then we are going to go and predict something. So let's say I want to predict for the 2020 Olympics. Then how do I do that? You just have to take a variable. Let's call it X underscore 2020. And then we're going to use np.array, and this time we are going to write 2020 to it and use the reshape function like we did because it's x-axis. So we are reshaping it and creating this type of a thing you can see. Now once this x is ready, I need to pass it to the model.predict function that we created because it's already created right here. You can see model.predict and model.fit. So this model object is already fitted onto this regression line, and we just want to predict now. So model.predict, and we are passing x underscore 2020 into it. And as a result, let me run this. Okay, let me run this one first. Okay. So I've run this one, and now I'm going to run this one. And you can see it predicts 9.52 or 53. So what happens here is this is 9.52. It is predicting that this must be something for the year 2020. And it could be a close approximation of what might actually be the number of seconds for the Olympic gold medalist for 100-meter race in 2020. So this is how you can use linear regression to make predictions and also to fit your data onto a regression line. I hope you understood all this, and I'll be back with the next video. So I'll see you there, and thank you for watching.